I welcome all the participants for the continuous professional development program on machine learning application to the optimization based control. For today's session, that is optimization in fuzzy logic control for robotic application. Today with us, Dr. Anupam Kumar, currently working as an assistant professor in the Department of Electronics and Communication Engineering from National Institute of Technology, Patna. Recently joined, that is 21 October 2022. Prior to this, he was an assistant professor in the Triple IT Kota and Triple IT Bhagalpur. He is currently working in the area of fuzzy logic system, robotics, signal processing, medical robotics, biomedical engineering, healthcare application, deep learning, machine learning. He received MTech and PhD degree from Indian Institute of Technology, Roorkee in 2012 and 2018 in the Electronics and Communication Engineering Department. He is a member of IEEE and published more than 14 SCI Scopus Journal, 10 conference, 2 book chapters, and 1 patent granted. He also published one book entitled as Tracking Performance of Maglev's System Using Type 2 Fuzzy Logic Control. He is working as a reviewer in various journals like IEEE Transaction, Elsewhere, Springer, Taylor and Francis. He also reviews in many conferences. He is also received a Best Paper Award in NIT Kurukshetra. He has attended several workshops and also participated in many research activities. Thank you, sir. I hand over the session to the Dr. Anupam Kumar. Over to you, sir.
Thank you, Professor Girish. Nice introduction. So now I will start. I think my slide is visible now, I hope.
Yes, sir. Yes, sir.
Okay. So in today's session, I will try to explain few things related to fuzzy logic, and then two type of fuzzy logic is going on in literature. One is type 1 and another one is type 2. So first I would like to explain type 1, that is conventional one, which was proposed around 1965 by Professor Jade. So the Professor Jade is a well-known researcher in the field of fuzzy logic, and he was also a pioneer in this field. So around 1965. So firstly, I would like to explain the things related to what is the historical things related to fuzzy, so that the audience may understand what was the things, why it comes in the to the research and all. That's why I'm taking the historical background. This is my roadmap. So I would like to explain history and then introduction, then fuzzy logic, that is type 1. So first type 1 and its application. So type 1 and its application and type 2 application more or less similar. I'm talking about applications. Then how we can implement fuzzy in MATLAB. Basic introduction, not the detail. And then what is major differences between type and type 2, then robot application. So first I would like to explain type 1, and then the one paper I have published in around 2018 that I'm going to explain with robot application. Right? So he is a Lofty Jade, famously known as a Jade, LT Jade, and he has written one paper around 1965 that was citation about more than 90,000. Right now it is more than lakh citation it has. And but this technique was not new. Around 1965, it is not new. It is some infinite value logic or some other form of logic. It is available, and it was proposed by Tarkis and around 1920. But it was not famous at the time due to there is no mathematical and there is no proper link with the real applications. So Jade has come with the concept, and he has given a two paper, an extension of first one, and he has given most of the theory in this paper. Later on, many things was reported, right? So right now a lot of research is going in the field of fuzzy, like fuzzy can be hybridized with many other techniques like in controller design, which I am working on from last many years. Now I shifted it to fuzzy with deep learning techniques, right? This is a new challenging area. Still very less paper are available in this field. Okay, so but recently few researcher like Tufan Kumbhasar and various researcher has started working in this area, and I have planned to work on it also. So this will be the new research area in coming years, right? For with help of deep learning and machine learning, etc. Right? So before going to fuzzy logic, we must understand from where it was derived. So soft computing is a branch. I can say that it is big umbrella where fuzzy logic, artificial neural network, and ANN consists of DNN, deep neural network, and whatever neural network we are watching, right? A very deep neural network is coming in the market, right? Many Google also developed some other techniques related to neural network. So basic is inspired from the ANN only, right? So this comes under the soft computing itself, right? And next one is evolutionary computation, like optimization technique, various optimization technique we know, right? Like genetic algorithm is one of the oldest optimization technique and famous around 70s and 80s century, around this year, right? So evolution computing contain genetic algorithm, genetic programming, and many other languages, many other optimization technique, which is based on evolution means evolution of human things, right? So like GA is totally based on evolution, right? How we are evaluated from the I can say cell to human being, right? So basic one unit of cell, right? So this is a evaluation process. And another one is fuzzy logic. Fuzzy logic is again a different area in comes under the soft computing itself. Neural network is again comes under the soft computing, right? Probabilistic reasoning is again. So all these are the different area comes under the soft computing, right? So this is a bigger umbrella, I can say, that soft computing where these things we have, right? So the soft computing term was given by Jade itself around 19th century, around 1995, right? Around 1995. Sorry. So it was around 1960, but hard computing was given around 1995, right? Hard computing. So because people are asking what is soft computing, then if there is a soft computing, then there must be a hard computing as well, right? So hard computing was given by the Jade itself around 1995, and in hard computing they talk about the just reverse process of soft computing. If I suppose I want to take one example of hard computing, then I can say suppose we are interested in roots of any polynomial, right? Suppose 2 ax square plus bx plus c. This is your polynomial, right? Second order equation, right? So with hard computing, we can get some fixed value of x1 and x2 because it has two roots. Then we can get a fixed value of x1 and x2. That is hard computing, right? Hard computing stands for the result is not going to change. Result will be the same if you are doing n number of time. But in case of soft computing, right, this is about hard computing. In case of soft computing, what will happen? The different result we will get for x1, x2 for each time. Means uh, suppose first iteration, first time we are doing some different result we are getting, right? X1 star something, x2 star, and next time we are getting again different result, right? X1 star, x2 star, likewise. So what does mean? Means in it means we are getting a different value for each time, right? This is the soft computing, and hard computing is for fixed value, right? So this is a major major difference between soft computing and hard computing. If anyone asking you, you can just like explain like that, right? So people used to say why then people are going with hard soft computing if they are getting different result, right? So it has another other functionality like low computational cost and many other things. This comes under the advantages part, right? And this is hard computing. So hard computing, we have to go the mathematical thing. The same result we are getting each time, right? So this result is precise result we are getting, but here we are getting fuzzy result, right? So fuzzy, ambiguous result, we can say that, right? So this is a major difference between soft and hard computing. Soft computing means we are getting a different result for same problem. In hard computing, we are getting a same result for number of time if you are doing same thing, you will get a same result, right? This is the major difference, right? So now our aim is to focus on the fuzzy logic, right? Fuzzy logic is our aim. Rest of this is not our aim because the topic is fuzzy logic and its application in robotics mainly, right? So now I will try to explain what is the fuzzy and what is the uh, things, right? So mainly fuzzy, just reverse of fuzzy is this is fuzzy, then fuzzy means fuzzy one, right? Fuzzy if we talk about fuzzy meaning, right? Fuzzy means value, and crisp means fixed value, right? So in fuzzy logic, we are getting a value, but what is the advantage? We will see now. Suppose I am taking one example, very good example of apple, right? We have one apple, and in crisp logic, this is a crisp logic, right? And this is a fuzzy logic, right? So in crisp logic, we will suppose we are interested in the color of the apple, right? What will be the color of apple? Suppose this is the question asked by someone to the right through if the answer, if you're giving the answer in crisp logic, then answer will be if it is red, then we can say 1. If it is not red, then we can say that 0. This is crisp. We have defined the value, right? Means we are interested in color. So color may be the red, maybe other color also of apple, right? So dark red, green, red, light red. Likewise, we have apple's definition, right? Means if you're talking about color only. In crisp logic, we have a two answer only, 1 or 0. What does mean? Means if the color of apple is red, then it is 1. If color of apple is not red, then it is 0. So two logic we are yes or no answer we have, right? But this is the crisp logic. But in fuzzy logic, what different we are getting result, we can see that. So here you can see that in crisp logic, this is physically not realizable. Means physical, if we talk about physical thing, so red or not red, but physically it is not. Physically means practically I'm talking about, right? Practically. Now again I am asking the question, right? the color of apple. So color of apple may be light red, means not exactly red. Then red, exactly red. Then somewhat green, means not exactly red, right? Not red, not red. Likewise, we have many answer, right? Light red means very light red, right? So in practical example, I can say that a different type of answer we have in case of practical answer, right? So fuzzy logic is providing this opportunity to us, right? If it is red, is not exactly, suppose red is 1. Suppose, for example, red is 1, not red is 0. The in between we have the answer. Means in between 1 and 0, in between 1 and 0, we have many answers like uh, light red, dark red, and uh, yeah, uh, likewise, right? So here we must understand this, why it is important, why it become important, because we have a practical answer, right? So that's why the fuzzy logic comes in the picture, right? In previous and twist logic, we have two answers only, 1 or 0. Suppose we are interested in autonomous car, we want to make a program for the autonomous car, right? So in case of autonomous car, if we want to apply the brake, in twist logic we have two answers: apply brake or not apply brake, right? Suppose some obstacle is coming in front of your vehicle and your vehicle is autonomous, right? Then we have two answers only: apply or not apply. But in case of fuzzy logic, we have answer that depend upon the distance we can apply slow brake. Maybe it depends upon the distance between your vehicle and the nearest vehicle, right? So various examples we have related to, right? Okay, so now this is a generalized, this is all about the basic things related to fuzzy logic. Who are new in this field, they can easily understand what is the major differences, right? So now I'm moving to the next part, right? So this is mainly related to the control applications, right? However, these four steps around steps we are performing while calculating or by applying fuzzy logic. This is your type 1 fuzzy logic, right? Just I explain type 1 type just I explain type 1 fuzzy logic right now, and later on, if time permit, I can go for the type 2 as well, right? So here you can see that here we have pre-processing and post-processing block, right? Pre-processing, post-processing, we will see what is that. Before that, we must understand what is in between, right? So here you can see fuzzification. The first important block in fuzzy logic system is fuzzification, right? In fuzzification, what we are doing, but here we have crisp value. What is crisp stand for? The practical value we have, like 1, 2, 3, likewise we have, right? And when we are applying this crisp value to the fuzzification block, this crisp value converted in fuzzy value, right? Fuzzy value. And this fuzzy value, again with help of rule base and inference engine, we are getting some rules, right? On the basis of given rules, we are getting some predefined. Actually, the rule base and is a predefined data set which is available in your fuzzy logic system. However, the rule base was generated by some expert knowledge, not randomly, like as per your application we are generating the rule base. We will see what kind of rule base we have, right? And an inference engine used for the firing, what kind of strength we want to fire, that depends on inference engine. We will see again two type of inference engine available. One is TSK, Takagi Suguno kind, another one is a Mandani type, that we will see step by step, right? And the fuzzification, again the part where we are converting fuzzy value, whatever here it is fuzzy value, right? Fuzzy value to the crisp value. this converted in crisp value with help of defuzzification. Again, right? Defuzzification block can be done with help of centroid or various defuzzification methods are available in literature. If you go on Wikipedia and search it, what kind of defuzzification techniques are available in literature, you will get n number of techniques, right? So mostly we are using the COG, the center of gravity defuzzification method, which is mostly used technique, most used technique in the literature, right? Because it was giving a better performances compared to the previous one, and it is also easier and lesser complex. But yeah, no doubt it has complexity, right? But performance wise, it is good. And at last, we are post processing the whatever this value we have. We are post processing with help of. So for now we have a prior knowledge about what is fuzzification, rule based, and defuzzification, right? Now our aim is to understand what is pre-processing block and what is post-processing block. So pre-processing block mainly used for whatever the physical quantity we have, physical or practical quantity we can say, converted in crisp value, which is applicable for this fuzzifier block, right? Suppose our fuzzification, in fuzzification we have membership function, and it was defined between -1 to 1. So we have to move this this physical quantity. Suppose physical quantity around 50 we are getting, some 15 volt we have. So we have to normalize in the range of -1 to 1. That can be done with help of pre-processing, right? And similarly, because of here we have done normalization, then we have to denormalize it. Then again, post-processing block can make it, because this is in lying between -1 to 1, then we have to again go back, convert it in the physical quantity like 50 volt, right? So it depends upon the fuzzification block, we will get another value that is 40, right? So that was done by, that may be done by the pre-processing block, right? And in case of type 2 fuzzy, what is the major difference between type and type 2? If we have a type reducer, you see, we have type reducer where we are converting type 2 to type 1, right? And so the same block, same thing we are doing with type 2 as well, but major difference between is type reducer. And everything is going to change now. However, the fundamental concept is remain same, but mathematically and the programming point of view and right, things are going to change, but conceptually it is remain same. Okay, great. If you have any doubt, if you feel, you can ask, right? No problem. Okay. Now here you can see that again crisp input, the fuzzifier block, because this is type 2, then it will it has a type 2 fuzzy sets, then rule based inference engine, similar like type 2. Here we are using the type reducer in order to, because we have to obtain crisp output directly. We cannot use defuzzifier block. Here we are using the type 1 defuzzified. The defuzzified cell. A different type reducer available in the literature. Most was given by the Jerry Mendel and Oscar Castillo, right? Most of the things they have done. So yeah, so okay. So this is all about type 1 and type 2 basic fundamental system, right? And how it works, everything we will see in this slide only. So here you can see the pre-processing block is used for quantization in connection with sampling and rounding integer. That is again one task if we are working on this task. Normalization are scaling onto a particular standard. Normalization, just I talk about, right? Filtering in order to remove noise, that maybe the some noises are coming in the input that can be removed by the filtering process. Pre-processing block also has such functionality. Next one is differentiation. So differentiation integration is when we are designing a different type of controller like PID, fuzzy PID, then we are required differentiation integration, right? Okay, and if you are working in digital way, then discrete time approximation is required. Okay, so this is about pre-processing, and similar kind of stuff we are doing with the post-processing block as well. Okay, now we are moving to the fuzzification block, right? So just I explained, fuzzification block mainly used to convert KISS value like physical quantity. I can say that KISS value means 1, 2, 3 kind of to the fuzzy value. Fuzzy value are not like 1, 2, 3, right? It has some membership grade, attached with some we can say the membership function, right? Membership grade with membership function. Likewise, it has, right? So fuzzification block evaluate the input measurement according to the premises of the rules. Each premises produces a membership grade, right? So just we will see how it was, right? So different type of membership functions are available in literature. Here we will demonstrate few of them, like triangular membership function. Here you can see that this is a triangular membership function, means triangular form, right? And this is the equation for a triangular membership function. Here you can see that this is the equation for this. This is the x less than a, 0. In between this, we have this equation x a to b, right? And b to c, we have a, b, c, d, likewise, right? Sorry, c. So this is a triangular mapping function. It can be written in mathematical likewise with help of line equation. This is a line equation. Again, this is a line. This is again a line. So with help of line equation, we can write the triangular membership function, right? So another, why we are studying this membership function, because in classification block we have a membership function, right? Next one is trapezoidal membership function. Again, this is, you can see this is trapezoidal form. This is for x less than a, then 0. Then in between we have this is a straight line 1. Here you can see the straight line. Again, this is the equation, and likewise, right? So this is just an introductory way. If you are new in this field, you can easily understand that different type of membership function are available in literature, like Gaussian member function. You know, the Gaussian is one of the famous uh, things, right, in our engineering field, right? Gaussian membership function is also available in the literature, and that can be defined with this mathematics, right? This is again a membership function itself, right? Next one is generalized Bell membership function. This is a Bell kind of structure, right? And that was this has a formula 1 plus x minus c. C stands for this your mid value, and divided by a power 2b. I think it is not visible. I can write again. Okay, likewise it has, right? Divide by 1, divide by likewise. So this is your Bell membership function. Okay, so this is all about the membership function. And what is the rule base? Rule base, suppose if you talk about two input, right? Mostly in controller design, when we are talking about controller design in fuzzy logic applications, then the two input we are using. More than two input, it become very difficult to handle, right? That's why in literature mostly we talk about two input only. Negative and change and error is negative. Then output is NV, right? What is that? This is a rule base, and it is generated with help of, I can say that who are expert in this field, they can easily generate the rule base, right? And it is mainly based on the your what application, on what application you are going to apply this fuzzy, then depends upon this rule is depend upon that one, right? So you can see that this is a one kind of matrix we are getting here. You can see that this is symmetrical kind of symmetrical type of matrix, right? NB, PM, PB, right? So this is one of the fundamental and famous rule base, and this type of rule base we are using in your literature most of the time. If you're not good in designing a rule base, you can simply take this one and apply your technique, right? Next one is inference engine. Inference engine I just shown in your previous slide, right? Inference engine is a block where two type of applications we are generally using, that is Mamdani application, and next one is Sugono. Okay. So Mamdani and Ashelian is one of the scientists who developed this technique, right? And famously later on this become famous with the name of Mamdani fuzzy inference system. It was developed around 1975, and right now also in controller design we are using Mamdani n number of times, because this is one of the way we are applying, one of the way in inference block. So first attempt was done for the steam engine and for the boiler combination, right? For the steam engine, for making a steam engine, right? Around 1975, most of the things related to steam engine only. So this was developed by Mamdani and Esselian, and he has given one technique, and the technique famously known as Mamdani. Next one is Sugono fuzzy model. This is a Mamdani fuzzy model. This is Sugono, and also known as a TSK fuzzy model, Takagi Sugono Kang fuzzy model. That was given by Takagi. Okay, Takagi, Sugono, Kang. These are the scientist name. Takagi, Sugono, and Kang was the scientist name. This they have developed this technique that is known as Sugono fuzzy model, right? And they have given some systematic approach. So in here, what we are doing, and what here we are doing, here you can see that when suppose we have two input x and y, right? Then z, then output will be the combination of x and y. But here it is here it is a combination like ax plus b y kind of combination if a and b are constant. Here it is not like that. It is a fixed value, depends upon a and y, just like that. If negative big, then negative, then it output will be the negative, like we have here. We have value, right? So I will explain how it works, don't worry. And next one is defuzzification block. So defuzzification block, again, you know, again one of the main block, not a main block, but it was used for converting crisp value, fuzzy value to the crisp value, right? So because when we are applying this controller to the some plant like motor control, like robot control, like many other applications, right? So we have to change the fuzzy value to the crisp value, and that was done by the defuzzification method, right? Is the process of conversion of fuzzy quantity into the precise quantity. Precise stand for crisp also, right? Right. So fuzzy quantity को crisp में ये all the step we have to perform, like fuzzification, rule based inference, and this step we have to perform whenever we are applying the fuzzy in any application. Most of the time we are applying fuzzy, then we have to do this step, because we have a crisp, then we have to convert it in crisp at the end. Otherwise, that logic will not work, right? So just I talk about the defuzzification. Various defuzzification approach are available in literature, like Max membership principle. This is one of the approach. Centroid method is one of the approach. Just like this is a centroid, COA, right? COG also. COG, it is also known as center of gravity or centroid method. Yeah. This is a centroid method formula. I'm not written all the formula because this is a famous one, so just I wrote, right? Here you can see that the membership value grade multiplied by z, right? Likewise. And weighted average method, again another technique. Mean max membership function, where we are taking the mean and max, and then center of sum, whatever the center we have, we are taking the sum of that one. Center of largest area, which one having the largest area, that center we are going to take. First maxima and last minima we are doing, right? So in similar fashion, we have n number of defuzzification technique in the literature, right? So as per our, I can say that people used to ask me which defuzzification technique is best one, right? Yeah, there is no, or I can say that there is no right answer for this, right? Because it depends upon totally the application, what application you want, right? Suppose you want fast application, means your applications is like we require in millisecond, in microsecond, we want this fuzzy controller work, right? Then we may not go for the this CUA because that may take a time, right? Then we have to go in such method as just like center largest area. We have to search center and largest area, that become a fuzzified value, defuzzified value, right? It will take lesser time. Okay, so it depends upon what application. Suppose we are applying this controller to some application where time doesn't matter, right? Then we can go for some layman, very accurate defuzzification technique, right? So it totally depends upon the application. If the application require a lot of, it depends upon requisition. If the fast, we require a fast application, then we have to go likewise. If we require slow, means it doesn't matter, it takes 1 day, 2 day, like that, right? So accordingly we are designing the defuzz technique, right? Okay, however the fuzzification is same for all, but defuzzification is different, depends upon the the application, right? What application we are going. Okay, so now this inference engine, we have two type, Mamdani and Sugano. Mostly we are talking about these two technique, right? So here you can see that the Takagi and Sugano and Kung developed this technique around 1985. In the paper was published in IEEE Transitional System, Man and Cybernetics, right? So, and here you can see then Mamdani and Assislian. This technique I'm talking about. It was published around 1975, right? The name of this paper is An Experiment in the Linguistic Synthesis with a Fuzzy Logic Controller, right? Right. So 1975, and still, still we are using this this technique, because there is no. I can say that I also use this the Mamdani and Sugano in one of the application. I use Mamdani. In one of the application I used Sugano. However, other techniques are also available, right? But because this is a famous one, and generally most of the researchers are using that one, that's why I also use. But because another why I took that technique, I have another answer also, like because it is well explored technique, right? If you're using simply this one, no one going to argue in your review or comment, right? So however, simply using simply if you're using simply this technique and applying some other some other new controller, then the the things going to be different, right? So here you can see that the Mamdani, how it works, right? Suppose this is a two input, I am talking about two input. So this is a one input X and this another input is Y, right? Okay. Here, okay. So here you can see that the input A, input X, cutting this membership function around this location, and here it is cutting this location, and the Y is cutting this membership function. This membership function is around this. So the Mamdani is based on Mamdani fuzzy inference system, has many way we can do. Like here we are using mean and max operation. Mean means first we are taking the mean. So the mean of this and this is this one, right? So mean of this one is this, and next one is you can see the mean of this and this one is this, right? Again we are combining both this one and we are getting this technique. So here we are doing mean operation, here we are doing max operation, likewise, right? And ultimately we are getting this output, right? This is your ultimate output. So here you can see that this is not kind of AX plus BY kind of thing we don't have. This is a Mamdani fuzzy, right? Here simply the depends upon the output membership function, and depend upon the which one is minimum, we are taking this one, right? Here you can see that this is your final output, and because this is a this is a distributed right? So because we require crisp value, then we have to pass it through defuzzifier, right? So defuzzifier, what defuzzifier doing with help of center of gravity method, or center of gravity, that is known as center of gravity method, right? COG, a centroid method. So we will get some fixed value, one value. Likewise, this is a suppose this is a 10, right? Here we have distributed value. Now we have 10. So this is a defuzzification, right? So this is a Mamdani approach. Next approach is Sugno-Fuzzy model approach. What is Sugno-Fuzzy model? Here we can see that again this one and this one. So minimum operation, right? So what is W1? W1 is based on this one. So output will be P1 and Q1 is a constant, right? So P1 of X, P2 of Q1 of Y plus R. This is the Z1. Similarly, Z2 we can have, and at last when we are adding both with help of weighted average method, because this is a the discrete value we have, then we have to use the weighted average method. W1 Z1 plus W2 Z2 upon W. The same way we are performing in the center of centroid method. Centroid method also is similar type, right? But because this is a continuous way, that's why we are using centroid. If it is discrete, then we have to use this way, right? So I hope यहाँ तक सबको clear होगा. Okay. If you have any doubt so far, you can ask. Okay. So now we'll see some applications related to the fuzzy logic controller. Okay. Yeah. So various applications are available in the market, like the in aerospace industry. Right. Suppose right now I'm working on drone application also, right? So in drone application, what we are doing, we are making controller for the robo or for the drone, where we want to control the altitude of the drone, how far from the ground it will fly, and the stability, how hovering of the drone must be stable, and various things we are doing, right? So this is also one of the application in satellite application, the altitude control, right? The altitude control of satellite can be done with help of fuzzy control. And UAV and autonomous drone mode, right? In both the things we can do, and in defense application also we can do, right? Okay, this is a aerospace application. Other application in, suppose we want to make regulate the room temperature with help of air condition, right? So that can also be done with help of fuzzy controller, right? One of the best application in your home, you can see that the washing machine is one of the best application of the fuzzy logic controller. You can see that the autonomous automatic washing machine. If you go and see your washing machine available in your home, that may be written the fuzzy based automatic washing machine, right? So here also in temperature control that can be used. So here you can see that when we are controlling the temperature in room, it has two parameters: temperature, what temperature you want, and humidity. Humidity is one of the challenging issue these days, right? Because if the temperature is normal around 25 degrees Celsius, then humidity may be changed, right? So that controller, and now PID controller can also do same stuff, but fuzzy, we are using fuzzy in order to robust application, right? Why fuzzy controller? People used to say, why fuzzy? Because in case of PID, the conventional controller, if you talk about, the PID controller has many. One of the best thing with PID controller is simplest one, right? And nowadays also 95% I can say that industry people are using PID controller, right? But it was seen that when the parameter of the plant, like AC, we are using AC for a longer time, more than 10 year, 20 year, right? Likewise. Then as time passes, the parameter of the fuzzy of the plant may change. Like if we talk about AC, then there's some parameter like resistance, capacitance value. If it is digital, however, some resistance or capacitance are there, they may change as time passes, right? So the older controller like PID, they may not cope up with the changing environment, right? Changing condition of the plant, right? So fuzzy has some functionality, then they can adapt it. However, PID also has, but fuzzy has better way, right? They do not. Then one more, I can say one of the best thing with the PID fuzzy logic controller is that do not require the exact mathematics of the controller, exact mathematics of plant. Right? They do not require. They require only the what output you need, right? If you want to stable output, then fuzzy can easily on the basis of output they can work, right? I can say that fuzzy works like a black box for some plant, right? We can say that fuzzy take a plant as a black box, right? Any kind of plant you can linear, non-linear, any kind of plant they can stabilize. However, depends upon the plant only. As it is not like that. If you have an unstable, highly unstable, and that cannot be controlled, then it may not control, right? But most of the time we are controlling such plant which we are using in physically, right? Next one is application. If we talk about automatic car driving system, just I explained. Suppose two car approaching to each other, then in case of crystal logic we have two answer, 1 and 0, right? 0 stand for brakes, 1 stand for not applied brake, right? But in case of fuzzy we have various answer, like how far it is, close, far, uh, more, far, likewise nearer, kind of function we can make, and we can we can make such a day so that the physical way we can work, right? Similarly, the traffic control application, right? Traffic control application may have this fuzzy techniques, right? So next one is the decision making of their business, right? Fuzzy logic helps in entrepreneur in the decision making process in their business. So most of the time you can see that fuzzy also used by the MBA people also, right? For the stock market prediction, right? That may be the cases, right? And next one is vacuum cleaner, also one kind of plant it has. So fuzzy may help answer, right? And the oven, right? Once we set the time in oven, if we needed it really fast, fuzzy logic help you out in this scenario. It helps to setting time in the machine. Right? So a washing machine is also, just I told you, the washing machine is one of the good example of the fuzzy application, right? Okay. And other application, milk optimization, means milk pasteurization. In case of milk pasteurization, we are using the fuzzy right? And in for the controller applications. And important is it can be used in image processing, signal processing as well, right? Where video camera are set to automatically capture the scene with their automatic exposure. Means we can make some video camera where as per your requirement they can take the picture. And speech recognition, facial characteristic recognition, that may be the applications of the a lot of research, a lot of paper are available in this domain related to the speech application, right? Okay, speech and facial applications. And if we talk about other applications like anesthesia, right, can be fatal in rare cases. So just I published one paper right in this year only. We are using the arterial pressure control, right? Arterial pressure of patient, right? What is that? Suppose we are injecting some anesthesia to the patient, right? And the anesthesia, how what quantity you can inject in your patient, in the patient, right? So that may be the control by the physiological controller by the by the this is known as arterial pressure control, right? If you go and see that, I have two paper recently. We have two paper on this arterial pressure control, right? And various neuropathological model can be drawn using FLC. That is help, like Alzheimer patient, maybe we are using such fuzzy, right? Fuzzy also used for diagnosis of diabetes or cancer patients, right? And in railway application, automatic braking, stopping a train, can also be done with help of FLC. Right? Underground train management is also can be done with FLC, chemical industry, and the robotics. Robotics are having a lot of, I can say that, challenges, because the robotics is very complex, right? Compared to the other technique, other application, robotics has many challenges, many parameters. If you are talking about 2D, then two controller you are required. If you are talking about 4D, then maybe require more than 4 controller likewise, right? So it has a lot of applications in literatures, right? So uh, next part, I'm going to discuss about uh, few very basic, then go back to the robot control applications, which I implemented in MATLAB itself. So before going to MATLAB, means the robot with MATLAB, we must understand how the fuzzy logic toolbox working in the MATLAB, right? So this is your MATLAB, okay, and this MATLAB having a Simulink, and in this Simulink section we have fuzzy logic toolbox, right? So fuzzy logic toolbox can be I can say that can be developed by ourselves also with help of MFile, or we can use directly from the MATLAB, right? So here in toolbox, if we talk about right, in toolbox, the fuzzy interface system having many blocks, like FIS editor, membership function editor, and rule editor. These are the editors, right? But these are the viewer, like rule viewer, view, and surface view, right? These are things are available in your MATLAB, right? And this is a fundamental block diagram of fuzzy editor, right? So I hope this this thing is new for you. If not, it's good. If it is new, then you can try to understand how it can work, right? So this is a here we are making this is a Mamdani kind of, right? So this toolbox, having all the functionality like Mamdani, Takago, Takagi Sugno, and etc. Right? However, you can make your own uh, own uh, whole code and work on it, right? This is your membership function, right? Here we are using the kind of Gaussian kind of membership function we are using, you know. And this is a rule editor where we are making a whatever rule we have seen, that is fed here, right? So here this is a rule viewer. What rule we are talking about? If you remember, this is a, you know, then this type of things we are getting. Okay, so now I'm moving to the the control application, right? So Okay, so okay, so now in this second part of talk, I would like to explain the basic fractional order. Why? Because I have developed one controller with help of fuzzy logic that require a fractional thing, right? So here you can see that what is fractional order system, and then we can go for the fractional order also, right? So fractional order system was not a new. It was developed around. It was talked about around very early, right? Around I can say in 19th century itself. Fractional order calculus is the area where mathematicians deal with derivative and integer of non-integer order. There are different. I can say that various definitions are available in literature. Some of like Grunwald-Lettinger definitions, Cauchy integral formula, Capito definitions, and RL definitions, right? Likewise, we have, right? And Oslo recursive approximation. Okay, Grisha, someone is unmute, unmuted, right? Please see that. Okay, great. That's okay. Okay. So again, I have to repeat because it is muted. Some I forget to unmute itself, right? So before going to discuss about the fuzzy controller, right? Because I used fractional in this fuzzy applications. So again, this is a new research area for the researcher. Most of the controller engineer started working this area. When I started, very few are working, but right now a lot of people are working in this area where we talk about the fractional thing. Means the the famous controller is PID controller, right? So PID controller like has one the indicator have d by dt, derivative have power, which is 1, 2, 3 likewise. But in fractional order system, we have power with fractional order, right? 1 by 2, 1 by 3, 3 likewise also. So, however, this technique was not new. Fractional order was developed at the time, was talked about at the time of Newton and uh, at the time of Newton itself, right? But because of there is no proper there is no proper computational techniques. I can say that specifically I can say computational technique because it took a lot of time while doing with manual way. Manual way is very difficult to do, right? So the yeah, if you talk right. So because of this computational era is faster right now. So that's why this technique become famous nowadays, right? And however, this technique was not new. I'm talking about fractional technique, right? So right now I'm using in our research work like mostly the Oslo recursive approximation. This is one kind of filter, right? One kind of filter that is IIR, infinite impulse response type of filter, right? This is IIR filter. The concept was designed was inspired from the IIR filter itself, right? That is known as and that is filter that is used for the designing of this. If you are interested in d by dt 1 by 2, then apply technique Oslo recursive approximation region. The first paper I can say that proposed by Paudel Benning around 1999, and they have demonstrated this flexible structure. Flexible stands for initially we have PID only. Now we have this structure. You can see that initially P suppose this x axis having lambda and y axis having mu, and lambda and mu is the power of integrator and differentiator respectively, right? So here you can see that if lambda and mu are 0, then it becomes P controller. If lambda is 0 and mu in 1 in this structure, right? Then it becomes PD. And if lambda and mu both are 1, then it becomes PID. If If mu is 0, because in x-axis mu is 0, lambda is 1, then it becomes pi. Right? You can see that. This is generalized. I can say this is conventional controller which we have seen in our in our BTech classes, right? P, PI, PID, PD, etc. Now the new things was introduced in around 1999 by Padal Bani. Just I explained that, right? Uh, uh, who has gave this flexible structure. Now, what is the flexibility in this? We can have the lambda in between 0 to 1 are more than 1. Mostly we are using lambda in between 0 to 1 only, are 0 to 2 maximum, right? Right. So you can see that now it become point to plane. P is a point, PI is a point, PID is point. Now it point to plane means this whole area can be used as a concept application, right? Suppose I want to use this area, then it may be Pi power 1 by 2, lambda power 1 by 2. Suppose this is a 1 by 2 and this is 1 by 2, right? So this concept makes the flexible structure. This is one of the fractional application. Fractional, again, fractional is having a big research area. I can say that a lot of work, a lot of research work in image processing, various areas we are getting, right, because the physical, till now we have seen the derivative and all in derivative and integration in only in the integer order multiplication, right, integer order only. But because of this concept, we have a fractional order also. So our physical system can be realized with help of these techniques as well, means the fractional order technique, right? What we are using like what I done in my paper. I can show you, right? This is your Ausloop recursive approximation, right? Here, one of the approximation technique as power lambda. Lambda is in between 0 to 1. How can be approximated with this particular concept, s plus omega s plus, this is a pole and 0, and this value can be calculated with help of this formula. This is one kind of IIR filter, right? Right. So I'm not going to detail of this. This is again a different domain, right? Okay. So now I can this paper I was published around 19 sorry 2018 17 18. That was my second or third paper, right? So this was design and implementation of fractional order fuzzy pre-compensated FOPID controller. What was new in this paper? It is a fractional order enhancement with pre-compensated controller. Till now, we have PID controller, FOPID controller, fuzzy FOPID controller. What we have done, we have integrated this pre-compensated and applied to 2D, very simple robot manipulator, right? 2D. After that, I went for the 5D as well, likewise, right? So 2DF, if we talk about 2DF structure, right? This is your 2D DOF. It has one link and this and another link. Link 1 and this is your link 2. This dark line is link, right? Dark and bold, I can say, right? So this is 2D OF. Here we have manipulated tip, right? You can attach some payload here and you can move from here to there, right, as per your requirement. This is simple 2D robot manipulator, right? DOF stands for degree of freedom, right? Degree of freedom, if we talk about definition of degree of freedom, we can say that the in layman, right? He in how many direction it will travel, right? That is your degree of freedom. Very layman definition, right? I'm not going to theoretical definition, right? Okay. So this is your simple 2D because it can move into this is, you can say this is a plane, right? In plane it can move here at x and y x way. That's why it is 2D plane. This is a planar robot, simply plane. It can move in planar. That's why its name is planar, right? Okay, so with help of Lagrange and other conceptual technique, we can have the formula, that is a mathematical formula, right? Tau 1 and tau 2. So what is tau 1? Tau 1 is torque applied to the torque, that link 1, and this is torque applied to link T2. And this is torque itself your uh, controller output, right? Right. And length, if you talk about length, we took L1.8 meter, L2.4 meter, and M1, M2 is around 0.1 kg. This particular mathematics was taken from the one of the famous book written by J.J. Craig. You know J.J. Craig. You are familiar with robotics. Then J.J. Craig is one of the famous scientists, one of the famous researchers in this field. Right? This particular 2D of structure was taken from this book only, right? And we have simulated in MATLAB with help of this mathematics, right? Here you can see that theta 1 dot, theta 1 double dot is stand for the derivative, right? Theta 1 first derivative, theta 2, theta double dot is second derivative, okay? And here C1 stand for cos theta 1, C2 stand for cos theta 2, and sin S1 stand for sin theta 1 likewise, right? And rest of the parameter M1, M2 are your masses of link 1 and link 2, L1 and L2 are the length of link, right? Theta 1 and theta 2 is angle from the, this theta 1 is angle from x-axis, theta 2 is angle from this link to that link, right? This is theta 1, theta 2, right? Okay, so I'm not going again in detail of mathematics of robot manipulator. If you are interested, you can go read the famous book by J.J. Craig. You can find it. It is again a separate research topic, right? Mathematical derivation of mathematics for you can generate your mathematics as well. If you have any idea of any kind of robot or any kind of manipulator, 2D or 3D, or you may have for your robot hand as well, right? Right now I'm working on robot hand, the hand for the some amputee kind of people, right? This is my biomedical application, right? So in this application, we have to make our mathematics, right? This is again a challenging task, right? Okay, so here you can see that this is our pre-compensated fuzzy logic controller, right? So this is your PID controller, simple PID or FOPID. This is a KP, KD, KI. This is a PID, and because we are working on the fractional order, right? That's why we have integrated fractional part as well. So here this is a derivative part, d by dt, and because right, d by dt minus gamma 1 minus, this is a kind of 1 upon d by dt, right? D by dt. So this is a integration itself, right? That's why it is written likewise. Okay, and we have added fuzzy precompensator prior to this particular controller. So what is the advantage of that? Any fluctuation, suppose any kind of fluctuation we are observing at output. What kind of fluctuation? Suppose any sudden change in output, right? Any something happened with in input as well, desired trajectory or some output, then this your error is going to change. Error, what is error? Error is the difference between the reference trajectory minus the obtained trajectory. Theta, this is your error, right? The reference trajectory minus that obtained trajectory, and that error is going to be changed if any fluctuation or any unwanted signal or we can say, right? So this fuzzy precompensator can compensate if any such type of changes like overshoot, undershoot kind of things we are observing at output sudden, right? That can be handled by precompensator. And this is a again this precompensator technique was taken by one of the paper by Keyman kind of researcher. They have the Chinese people, they have developed this technique. So we have hybridized both the things, and we have this new fuzzy precompensator, right? So here you can see that this again we are getting some theta pre, and this theta pre means the precompensated output again applied to the PID controller, that is FOPID controller, with help of your output, right? So whatever the obtained output is again subtracted with the the generated new pre-compensated reference input. That is your theta t reference input, and this is your theta t output, obtained output, again differentiated, and we have, we are getting some new error, and this new error is fed to the your PID controller. I can say FOPID controller, and this FOPID controller generating some control signal. That control signal is this control signal not only the control, it also the torque. That is a torque. Right now because this is a simulation work, so we did not consider the motor here, right? If you are having motor, then this controller is going to be in motor. Motor is generating the torque, and the torque, due to the torque, your manipulator manipulator link is going to move. This link is going to move, right? So because here we are considering that whatever the torque, whatever the control action, the motor is generating the torque as per control action, right? And that torque and control action, if we are neglecting the motor, then torque is equal to the control action, right? So that's why we have neglected it. It doesn't matter, right? When we are doing the simulation, but if you are going for the hardware application, then it require, right? Because otherwise the motor is not going to, your hand is your manipulator is not going to move, right? Okay, so this is your output at last, right? So you can see that UIT. So this is all the mathematics related to UIT. UIT is combination of FLC and the two input. We have just, I talked about earlier that most of time we are using FLC as a two input one. If we are going for more than two input, then we are facing challenges with three, more than two input, is that number of rules is required, computation complexity, integer, and many more things, right? And one more thing here I want to say, that we are using the integrator also. Suppose we are using integrator as input, then what challenges we are facing? Integral wind up problem we are facing. What is integral wind up? Integral wind up, when we are integrating something, right? We are suppose a small error we have, just like we talk about PID controller, PID, this PID, P just a proportional and derivative just differentiating whatever input we are getting. But integral, what integral role is that? If small error we have, very small error we have, then integrate and make it big, right? Okay, right? So that's why integral wind up concept comes in the picture in case of when we are using the three input, and where third input is integral, right? Then problem arises. That's why most of the time you can see that in fuzzy application we are not using the integral as an input in fuzzy. We are using as a separate entity. Yeah, PI, a PD, right? But most of the time we are, when we are going for the drive application, in drive application we are not using the PD, we are using the PI only, right? Because of some other issues are there, right? Okay, so here you can see that where we are. Okay, okay, here we are, right? This is a error, and this error is fed to this your controller, the PID controller, right? This is your robot, what robot we have seen, right? If we zoom this part, right, we can have such type of structure. You can see that first for the first link we have to make one separate controller. For the second link we have to make the separate controller and apply to the robot manipulator. Okay, a robot manipulator, whatever mathematics we have seen, this is your mathematics, tau 1 having first mathematics, tau 2 having second mathematics, and this robot manipulator having these mathematics. So simply in M file or what any in Simulink you can do, you can make your own code for this method of mathematics. This is not big task, very easy task, right? You can do yourself, right? Right? If any one of the researchers are facing any difficulty for doing such stuff, they can contact me anytime, right? And this is a membership function. Here we have considered triangular membership function, and this is your rule-based surface plot. We can say that, right? It is drawn between error, derivative of error, and output. That is control output. Okay. Because whenever you are developing some new controller are hybridized controller or novel controller, it has to be compared with your previous versions. That's why we are comparing with PID and conventional fuzzy logic controller, right? In order to show the superiority of your proposed controller, right? That is required. It has to be done. Otherwise, how you can justify that your controller is giving better performance compared to the rest of the controller, right? Okay. And the simple this is a fuzzification block which we have studied in our in first session, right? This is the same thing we have written here, and in this case we have taken some different type of rule base, because this is not exactly this is a pre-compensator. That's why we have to take this type of rule base. However, if you're taking a simple rule base, when I am working on it, I used simple time symmetrical rule base, right? Just like shown you in the first hour, right? So then also it will work. There is no big challenge, right? However, we have used this rule base because of this pre-compositor designed by some of the professor who has taken this rule base. So I just took that rule base from this literature itself, right? And here you can see that here you can see that in PID controller, because of two link, so we have required two controller, right? So 6 parameter we have to optimize. In case of fuzzy PID, it has 4 parameter for one controller. Integer order fuzzy pre-compositor, it has around 12, and in here we have around 14 parameters. Yeah, I think it is having 12, it is having 8, right? They're having 6. So such big amount, such a large parameter, it has to be true, and that cannot be done by the heat and trial process. Very difficult to do with help of heat and trial process, right? That's why people use optimization technique, right? So in this we have used artificial peak colony optimization. You may use different, like right now various GWO, ABC, PSO, various techniques are available in literature. You can use any one of them because this is a new one, very right. So I use that ABC in this technique. So I'm not discussing ABC means optimization technique in detail, because again it's a different topic, right? So I'm focusing on my talk on the controller and robot only. Okay, and this trajectory again you have to design, right? This is known as a trajectory generation, right? In simulation work we are generating a trajectory, but in real application, suppose your robot or your uh, some undefined trajectory, then it has to be generated in in real time itself, right? At the time the controller the controlling that particular means following this particular trajectory is again one of the challenging tasks, right? So here we have used cubical polynomial test trajectory for making a trajectory, right? This is a test trajectory in cubical polynomial in nature, right? So again, this is a cubic polynomial, right? So as per design parameter, we because we have two link, then we require two different trajectory. Here we use this type of trajectory we have. This is a first trajectory and this is a second trajectory, right? Sorry, this is this is first and this is second. So here you can see that we have to design this trajectory with help of this predefined constraint, right? So theta d1 at TSP 2 radian. What is TSP? TSP is 4. TSP is 2 second, 2 to 4 second, right? 0 to 4 second. We have considered around 4 second. So these basic things we have considered here. Here you can see that 2 radian and 3 radian for 2 seconds, and 0.5 radian and 0.5 radian for 4 seconds, and the theta dot and for the both 2 second and 4 second are 0. Why we are considering this one? Because at that moment, if you having, you know, the if you having changing, means there is some velocity at that moment, then it is very difficult to handle, right? That's why it is considered like that. Okay, so the trajectory, we are getting such type of trajectory. Okay, so what we have done, we have designed this controller and simulated and run a lot of time, more than 100 iteration run for each controller separately, and we are getting different results, right? So here you can see that very closure, right? So this is a trajectory tracking performance of the link 1 and link 2, right? So this is red one is for link 1, this is for link 1, black one, and this is for link 2. Okay, this is for link 1, this is for link 2, right? Okay, so because you know, PID, for the fuzzy PID, for the integer order, for the fraction order, we are getting closure result. That's why we zoom that plot separately. Okay, this is for the path traced by end effector. What is end effector? Suppose this is your one manipulate one link. This is your second link. So this tip is known as a end effector. This is end effector. So what kind of movement, if we are giving such trajectory to the theta one, this is theta 1, this is theta 2, right? So if we are giving this trajectory, this is theta 1, I can say this is theta 2. This type of trajectory, if we are giving for 4 seconds, then your manipulated tip is going to move likewise. This is movement of, right? Again, with help of some mathematics, we can generate this that path traced by end effector. Right? Suppose we want to lift this some item from this to this location by this route, then we have to give the trajectory in such a way. Right? Okay. This is the x and y coordinate with time. That is your x coordinate. This is your y coordinate. So how it is varying with time, that was given with help of this formula, right? And this is a control output with respect to time. But right. So what kind of controller, what kind of fluctuation we are observing at control output of the fuzzy, for the PID, for the all the things we are getting likewise, right? This is your position error. Means lesser for proposed controller and larger for the conventional one. Okay. Okay. So this type of study we have done with this controller, and what major challenges we have faced, that tuning of the parameters. Like, you know, we have a lot of parameters here, lot of parameters we have, you know, we have around uh, four, around 12, 14 parameter. Here we have 12 parameter, more than 2, because this is lambda and 3, because 3, so I think 15 over, right? Okay, so this doesn't matter, but matter is that the tuning of these parameters is challenging, and changing and selecting the range of these values, means what range you are going to take, kp 0 to 10. What about k? So again, sometime the algorithm may stop because of this range not taken properly. Again, so again, this is a heat and trial process, and finally we are getting the output, right? Here you can see that for the optimization, we have considered some objective function. That objective function is integral, right? It is known as integral time absolute, right? So we are just discussing the simulations results related to the very simple control techniques, which was proposed around 18 to 17. This is one of the research which, right? So uh, very basic thing we have done in this paper, right? And we have implemented many things, right? Because this is a new area, so we explore those things, right? And here you can see that the for the link 1, for the link 2, the integral time absolute error is lesser for the proposed controller, while for the PID and other controller we are getting some larger value. This is a pictorial representation, right? Because we are not getting proper uh, right key, which one is better, right? It is very difficult to answer here. That's why ITA as considered as a objective function is considered as a comparison purpose, right? So because whenever we are doing any kind of control design work, we are doing some robustness testing as well. So in this work also we have in this work also we have used right. I hope it's fine. Okay, so in this also we have used robustness testing with help of some parameter changes, as I discussed in first hour, that when time passes, right, some parameter of the plant may change, like resistance, capacitance, something, when we are seeking some the spring elasticity may be changed after 1 or 2 years. That depend upon the, right? So, so that's why we have forcefully changes, right, the parameter of the robot and try to understand what changes we are observing, right? So here we can see that we have changed a mass by 5%, not more than, not big changes, but only 5%. Similarly, we have changed the length, right? Sometimes we have increased, sometimes we have decreases, right? And try to understand that what was the changes in the ITA value. These are the ITA values, right? ITA values. And we observe that the changes in the proposed controller is very less. Here you can see that this is the pictorial representation of changes when we are changing the mass of the mass link, likewise, right? So again, changes of the proposed controller is lesser, while PID controller has a major, you can see the fluctuation we are observing in PID also and fuzzy also, but in this case we are getting a very less fluctuation, right? So this is one of the robustness testing analysis we have done with this one, right? Next is next is, sometime external disturbance, like you have touched your robot manipulator by some stick, something other. So external, you are giving some external disturbance, right? So that external disturbance we are adding at a controller output. Most of the time we are adding at a controller output only, right? So in this case also we have applied some external disturbance to the system. And this type of disturbance mostly is kind of, whenever talk about controller output, right, at that point we are generally using the sine kind of uh, generally we are observing sine kind of disturbance we are observing, right? That's why here we consider sine 50t because it has some fluctuation, right? Like likewise. So whenever we are observing, whenever we are applying some disturbances at control output, then it must be likewise, right? So again, we have applied to the link 1 and again link 2, and both the links simultaneously. We observed that the changes in proposed controller is lesser. Here you can see that is again changes in the proposed controller is lesser compared to the other controllers, right? Then we can justify that, yeah, right? Yeah, this is our controller is better, this, right? So first we have applied at link 1, then link 2, right? Link 2, and then both the links likewise, right? The first observed in link 1, what was the changes, link 2, what was the changes, and similarly when we are applying the disturbance link 2, what was changing link 2 as well as link 1, right? So such type of stuff we are doing in the simulation study uh, in robustness part, right? Again, because all the plot cannot be shown, so we have taken one 0.3 sine 50t as a disturbance, which was applied at controller output, and we are getting. So here can again see fluctuation in output is lesser. That cannot be justified here, but with help of this diagram, we can justify. Okay, so this is a simulation analysis. So if we talk about this paper, then what challenges, what conclusion we have observed that. So first is we have successfully tracked the trajectory, whatever trajectory we chosen, we have tracked successfully. And here we have implemented fuzzy precompensator to the controller in that will compensate any fluctuation, any the overshoot, undershoot, whatever, right? And we have done a robustness analysis, such type of, right? So this paper was published in AEUE, International Journal of Electronics and Communication, right, around 2017, and now it has a major at 3 impact factor. And because I'm talking about this paper itself, so here you can see that this paper has cited well, around 64 citations we observed, right? So this is not a big concept, but because of simpler concept and people is easily understand what is that, so people are using it and citing it, right? This is a thing I want to share here. Okay, and okay, so till now, sir, if you are starting some new topic now, it will take time, sir. I'm not going for type 2 now.
Okay, sir. Okay, sir.
So in this lecture, we have covered mainly fuzzy and fuzzy part, and it's one of the application to the robot application, right? And optimization, just I introduced optimization. What was the purpose of optimization is to tune the parameters, right? That thing we have just introduced. And if next time Girish sir is also inviting me, then I will discuss about type 2 in coming session, right?
Yes, yes, sir.
Sir.
Yes.
So this is all about my side, sir. Over to you.
Sir, when we are designing a robust controller, the optimality will be lost, and when we are designing an optimal control, the robustness will be lost. Is it true, sir?
Sorry, I can. I don't know right now. I think Girish sir can. This is a
Okay.
pure
Okay.
control,
Thank you,
right?
sir.
Okay.
Okay. Thank you, sir.
Right.
Related with fuzzy logic control application. Any question?
Sir, sorry, once again, sir.
Yeah.
Sir, validation of these fuzzy controllers, are there any standard methods to validate?
Where? Where
This
you want
fuzzy
to
controller,
validate?
sir, if we
Means
need to validate,
validate you want to ask that which plant you want to apply, right?
no, sir,
Something.
any plant, no, any plant, if we want to validate its performance, so is it
Okay.
again using traditional method or any other methods are there, sir?
If you are using fuzzy, then you have to go its conventional counterpart, not fuzzy with some deep learning technique, right? Not model predictive control. No, not like that. You have, right? If you're dealing with fuzzy, then you can go with their conventional counterpart one, right? What we have done in our research work.
Okay, sir. Thank you, sir.
Another question, sir. If the tuning parameter range is large, how to go about the tuning?
Yeah, if the tuning parameter is high or large, then we have to go to the optimization only. Other way, it is very difficult, right? So you may use any optimization technique which you are comfortable, right? And mostly people, what they do, used to do is that they are using some new technique, like which was developed recently, right? So You can take anyone as per your comfortability. But tuning by heat and trial process by some mathematical process very difficult if number of tuning parameters is large. Okay. Yeah, the same process, right? The optimization with help of optimization you can do. And I can say that if you are going for other technique, then it is very challenging, right? So I would suggest you can go for the some optimization process. All the codes are available on the GitHub and everywhere, right? Yeah. The hit and trial process is difficult. Yes, Sangeeta. Because the number of tuning parameters is large, right? No, it is very difficult, right? If the plant, in my case, it is difficult. Maybe if you're going for power grid, some other technique, then I don't know exactly, right? Okay, power grid maybe requires some other technique also. Because one of my friend in NIT Patna itself, they are working power grid. They talk about thousands of tuning parameter, right? Not related to controller, but some other. They are doing like that, right? Without optimization technique. So I don't know what way they are doing, but if we talk about controller, then I can suggest you must work with the optimization, right?
Sir, in autonomous drone, you have suggested this optimization technique for using fuzzy logic, no? So for autonomous drone, why
No,
this
madam.
system is okay?
Actually, this is for robotic manipulator application.
Yeah, we can use drone as well.
Drone application also, but in the presentation, robotic
Yeah.
manipulator application.
Yeah. Yes, ma'am.
No,
Please.
sir has shown one slide, na? In that slide, he has shown that autonomous drone, then that bus and all these things.
Right.
So that's why means that question raised in my mind that if you are talking about the robotics and all these things, then
Yeah. So
how this will
what is your question, ma'am?
actually for autonomous drone, this fuzzy logic when you use, and for robotics when you use this fuzzy logic, then what parameters will be changed, sir?
What parameter it change means I'm not getting.
Tuning will be different or what?
Listen. Actually, what we are doing is that if you talk about drone, right? Drone application again, we have mathematics of drone, right? So suppose we are interested in altitude control, in motor control, various things we have around three things we are controlling, 3 to 4 things we are controlling in drone application, right? So we require around different four controller, and again we have to tune it with some technique, right? Some optimization, hit and trial, whatever, right? So mostly I am preferring the optimization technique because they are just simply giving me your tuning parameter, right? Easily. Yeah, but if the task, if we implemented the controller in the drone in hardware application, then we cannot change, right? Because it is fed in your drone, right? But initially what we are doing, we are designing for in simulation and testing it and checking the performance, then later on we are shifting it in hardware. This is the way we are performing. Okay, Asam?
Okay. No, because you showed one slide in all the military applications.
This is application, right? You are right.
You are showing means I do not understood how the robotics parameters and these parameters will be
Actually, I'm talking about PI. I just say suppose I'm taking one simple example, PID controller, right? So PID has 3 parameters, KP, KD, KI, right? So again, the PID have 3 parameters. So tuning 3 parameters is very easy. But suppose we are having 4 or 5 controller, PID different 4 or 5 controller. Then 4 into 3 become 12. Then tuning 12 parameters is challenging, right? That's why I'm talking.
Okay, sir. Okay. Thank you.
Yes, sir. I think I tried to answer all the questions.
Okay, sir. Okay.
Sir,
I would like to I would like to thank sir for your excellent presentation. Your presentation is very helpful and beneficial to all the participants, and all the participants are motivated from your presentation as well as the demonstration of the fuzzy logic toolbox, which include the fractional order system, then optimization, then their application in the robotic field. This is very useful. Participants are tried to implement this type type 1 and fractional order fuzzy logic controller for various applications. Thank you, sir. Thank you very much.
Giri sir, I want to add a few things if you allow.
Oh, okay, sir.
Here, if anyone interested to work with me, any kind of research, right, they can contact me. Right now, I just joined NIT Patna recently, right? So I have opening for the full-time as well as part-time student as well, right? So right now the date is over, but in next session is July and right, that opening maybe at the time also. So you can forward your group if you're anyone interested, right?
Yes,
Right.
sir. Yes, sir.
Yeah, I can share my NIT Patna profile for your understanding, right, in chat box itself. Anyone interested or anyone want to work with me, they can contact me, right? I'm working in EC department right now, okay? And yeah, this is all about me. I just share the link to the chat box if anyone interested. If anyone, if any their colleague or their friend interested in PhD full time as well as part time, they can contact. Yeah. Okay, sir. Thank you. Thank you very much, sir, for
Thank you, sir.
your
Thank you, sir. Thank you,
invitation.
sir.
Thank you. Thank you.
Thank you, sir. Thank you, sir.